Hello and welcome everybody to the second video on this channel on the n particle system. Today we're going to be proving the conservation of momentum using Newton's second and third law. So let's get started. So let's consider the total momentum of the system. So we'll just call that big P right here. And the big P is going to be the sum of all the momentum of the alpha particles. So we'll just sum over all n particles here. And what we're going to do is take the derivative with respect to time of big P. So this is what we're going to analyze. And on the right hand side, the derivative of a sum is just the sum of the derivatives. So we're going to bring that derivative in. Oops. Let me draw a better sigma notation. There you go. Alpha equal 1. And we're going to have the derivative of the momentums. There you go, of the alpha particle. But as you can see, we already know what the derivative of the momentum is. This right here is precisely this, right? So we're just going to equate that. So the derivative of the momentum of the alpha particle is just equal to the net force. Perfect. One, and we're just going to have a square bracket where we're going to shove the net force in. We'll write this in white. Try to get some colors in here. Colors are appealing. They increase video retention. So I'm going to try to add as many colors as I can. So yeah, this is correct. So beta does not equal alpha of the force on alpha by beta. And we'll just close that off. Boom. Alrighty. So what we're going to do now is distribute this sum across both these terms. And that is just going to simplify into this. So in this first term here, the sum of all the external forces, we'll just call the net external force on the system. So this is just equal to the net external force on 1, plus 2, plus 3, whatnot. So we're just going to quantify that with just the net external force. No indices here, just net external force. And what we're going to get on the right-hand side, or on this term, is this double summation. This double summation is going to be the kind of tricky part in simplifying. I'm going to scroll down just so I can write this a little easier. I don't know why I can't write it. So alpha is equal to 1. And then we're going to have the interaction forces here. We're going to make the alpha index yellow, the beta index white. So you can kind of see what's going on here. So this external force term, we're just going to leave alone. We're not going to touch it. But this double summation here, we are going to simplify. And oftentimes when you have a summation and you don't really see what's going on, for example, a single summation, let's say of just 1 over n, just sketch this really quickly. You can just write this out as like a one-dimensional diagram, I guess. You can just say this is 1 over 1, 1 plus 1 over 2, 1 over 3. So you're just substituting n equals 1, that's a term, n equals 2, that's a term, yada yada. And of course, summations can be a lot more complicated than this. This is just an example, just to show you how you might visualize a one-dimensional summation. But in the context of a two-dimensional summation, well, then it's going to be a two-dimensional diagram. So right here, I'm going to write alpha in yellow. I'm going to have alpha 1, alpha 2, alpha 3, 4. And then here on the top, we're going to have beta. 1. You're going to make a little square grid here. And let's say that n is equal to 4. So we are going from 1, 2, 3, and 4. So these are the alphas, and this is the beta, right? And then here in each of these square boxes are going to be the terms. And this double summation is just going to be adding all the terms. And here we're just going to figure out what all the terms are. So to write this more explicitly, this double summation, you can think of it like this. So here we have the external force. And then here we're just going to explicitly write this sum here, at least for the, we're going to get rid of this first summation and just write it explicitly. So here we're going to have beta is not equal to 1, because that's going to be the first alpha. And then we have the force on 1 by beta. So that's going to be the first summation. And then we're going to have a second summation. You can see why it's kind of useful to write it in 2 dimensions, because you can think of this as the first dimension, and the sigmas are kind of have a second dimension of their own, and we're like combining a 2-dimensional sum. It's very, very tricky to think about, but you can use this idea to, I don't know, think about 3-dimensional sums, 4-dimensional sums, whatnot. It's all just extra dimensions. So here we're going to have the force on 2 by 1, or by beta, sorry. We're going to have beta is not equal to 2. And of course, we're going to go all the way up to n. And so on and so on. So the next summation will be beta is not equal to 3, and so on and so on. So here, let's just visualize what's going on in this diagram. If we have the first summation, which is going to represent the first row here, alpha is equal to 1, right? And we're just going to cycle through all the betas as long as beta is not equal to 1. So as you can see in this first one, we're going to have 0. The force, because that term doesn't exist. It can't. We made the condition that beta cannot equal 1. So that term is going to be 0. And this term is going to be the, I'm not going to be writing all the alpha indexes in yellow just to make this a little easier, because we're going to fill all these square grids. So this is going to be the force on 1 by 2. So that's what that term is. I'm not going to write the force as well. So just keep in mind that each of these boxes is going to be the force on 1 by 2, but we're not going to write the force because it's implied. And then we're going to have beta is equal to 3, so the force on 1 by 3, and beta is equal to 4. And that's going to be the top index because we're setting n equals 4, just for this example. However, you can think about this for arbitrary n all the way to 10 to 100, how many particles you have. We're generalizing this as much as possible. So that's going to be the first row done, the first summation. So now let's consider the second summation, as long as beta is not equal to 2. So we have the force, on 2 by 1. Remember, the 2 is the first index here. And then here we're going to have 0 because beta cannot equal 2. Then we're going to have the force on 2 by 3, on 2 by 4, and so on. And I'm just going to write all these boxes. So then we have the force on 1, force on 2, force on 3, and 0. Keep in mind, these are all the force terms. And we're adding each of these boxes together. And so by writing it like this, you can sort of see a pattern here. There's a symmetry here along this diagonal. And each of these forces will come in pairs, as you can see here. So we have 1 on 3 and 3 on 1. 3 on 2, 2 on 3. 1 on 4, 4 on 1. So basically, for every time we have, let's say, a force on 1 by 2, we're going to have this symmetry to consider, right? And then if we go on the other side, we're going to have the force on 2 by 1. And this applies to every single term here. So they all come in pairs. And this is obvious through the physical diagrams that I drew. So every time you create a particle, they're going to interact, and the force is going to come in pairs. You create another particle, it's going to create another pair on this particle, and it's going to create a pair on this particle. You add another particle, as you can see, it creates a pair for each of the particles. This particle needs to interact with that. As you can see, every time you add a particle, the forces will come in pairs. This is just Newton's third law. The Newton's Newton's third law will allow all these forces to cancel. And what we're going to get is that this term, so this whole summation, and this term right here is just going to be equal to 0. Isn't that cool? So this whole thing is just equal to 0. And what we are left with is going to be the fact that, remember, this is going to be the derivative of the total momentum. So what we are left with is the derivative of the total momentum is equal to simply the external force, because all those interaction forces are going to cancel. And this right here is kind of the conservation momentum. This is actually an even better equation than the conservation momentum, because it tells you exactly how the total momentum changes. It is due to the external force, the net external force on the system. So we could have just the external force on one particle, for example, like in this case. They're all interacting, but only particle 1 has an external force. Well, then that means we know that the total momentum is just going to change by that external force on 1. But let's say 2 also has an external force. Well, then we have to add that 2 as well. And then if 3 also has an external force, then we add 3. So just a net external force. And if there are no external forces on the system, so this is the best part, there are no external forces on the system. In other words, we say that the system is totally isolated. Is just equal to 0. And what we get is just P dot is equal to 0, which is kind of just a differential equation we can solve, which is very simple differential equation. We just say that the total momentum is just equal to a constant vector. And there you go. Total momentum is conserved if there is no net external force on the system. Thanks for watching. Hello and welcome back. This is going to be an attachment at the end of the previous segment. Just a little continuation here, little footnote. You can prove more formally the conservation of momentum by explicitly writing the sum like this. So you can go ahead and see for yourself that if you go along with this sum, that is actually the same thing as this. And in this version here, you can see explicitly that it writes each of the force pairs, and therefore we can immediately deduce that this is going to be 0. So this is just a more formal approach. I didn't include it because it is not very alluring, and it kind of just turns the complicated sum into a even more complicated sum. It's not really obvious how this is equal to that. But you can go ahead and show that this is indeed equal. Also, another footnote, when we went along with the derivation of the conservation of momentum, or the fact that the total momentum changes precisely due to the external force, at no point in the entire derivation did we assume that the forces were central. And I know that every time I drew a diagram with forces acting on these particles, they were always central, and that would mean that they lie on the line of separation, pretty much, so to speak. However, this isn't a necessary condition. For example, we could have forces like this. So this could be the force on 2 by 1 facing that direction, and this force is the force on 1 due to 2. As you can see, they are not in line. They don't lie on this line. They're not central forces. However, they would still obey Newton's third law. And that's the fact that the forces are equal and opposite of each other. So note that the forces do not have to be central in order for conservation of momentum to be obeyed. And yes, there are indeed some forces out there in nature that behave like this. For example, the magnetic force. The magnetic force will conserve momentum. However, angular momentum does depend on the forces being central. So the conservation of angular momentum. So in the future, we can prove that how the angular momentum changes is due to the net external torque. This relies on the fact that the forces are central. We cannot make any general statements if the forces are like this. So in the case of like magnetic forces like this, the translational momentum will be conserved, but the angular momentum won't be, because the forces aren't central.